Hello, my name is Alejandro Gandara, and this is my Eggstranauts Project 2 submission for Calvin Stewart's Mechanical Engineering Statics class at Utep. The objectives of this project is to use all our knowledge as engineers and what we gained from this class to design, build, and test a prototype lander that will carry an egg within its structure and survive a drop successfully. When survive that drop, we will calculate the velocity and the forces going through it through a structural analysis. The design requirement of our lander is that it must be made with spaghetti and have an egg secured within the frame and survive a meter drop. From here on, I will refer to the egg as Eggstranaut because it just makes me happy. The materials and supplies used for our lander is any commercial pasta that can be shaped, molded, or even boiled in water. Transparent hot glue is the only joining material allowed. However, it must not be used as a structural member. Recycled plastic bags may be employed with string to attach to the lander. Additional notes of our designs is we cannot paint the lander, we can paint our Eggstranaut, and glue is only allowed to be at the joints of the spaghetti, not along the strands. Maximum or minimum requirements of our lander drop, or our lander as a whole. The minimum drop height is 1 meter. The maximum weight of our lander is 450 grams. The maximum landing pad size is 300 millimeters by 300 millimeters, which is basically the area that our lander must fit into. My personal goals with this project is to survive and drop, is for my lander to be dropped from a 1.25 meter or higher and survive. I also want my lander to weigh less than 150 grams. I also, of course, want my lander to survive all attempts. So, given this project, brainstorming is a pretty important part of it. We were tasked to research and look at real-life Mars landers to inspire us and give us ideas onto what we will design our lander to look like. I looked at a bunch from the past, present, and even future designs so that it could inspire me and give me some ideas of what to build. I also looked at water towers, which gave me more ideas of what to do with trusses. So, which leads to my first design. You can see on top left there, and on the bottom left, you can see the Phoenix spacecraft, which was launched in 2007. My lander's design was built in a similar image to this spacecraft because it is NASA's 6th successful landing on Mars. It used 3 legs that had scissor truss designs and a bag to reduce the impact. Although a fault of this design is the fact that the legs aimed it to the seat of the egg right over here, which kind of put this design at waste, although it was a good design. Although I improved it so that my second design is still based off of NASA's Phoenix and utilizes the 3 legs and the scissor truss. Although with this design, the truss is designed away from the Eggstranaut. It will transfer the impact force away from it and outwards, which is fantastic. That was the whole point of it. It utilizes triangles for structural security and has a bunch of advantages, although I cut the bag from the design because I felt it wouldn't do much good from how little we were dropping it. My third design, however, I kind of went all out with it, and it was inspired by the Altair spacecraft. It utilizes its octagon shape, a generous amount of forelegs, to absorb the impact and displace it around the 8 sides of the octagon so that the Eggstranaut would not be damaged. The big issue with this design, though, although it has many benefits, is the fact that I couldn't at least figure out a way to build a seat for my Eggstranaut. I had a lot of issues of trying to figure out how to design it so that when it hit the ground, the egg wouldn't just pop out of its little hole and fall and splat. So I eventually went with my second design that I drew a better picture of on the right. It is still inspired by NASA's Phoenix and utilizes the strongest shape in all sorts of building supports and trusses, which is the triangle. It is effective for strong support and should successfully displace the impact away from the eggs due to how I designed the truss. An important thing to notice here about my design is that it is a tetrahedron, which is an equilateral triangular pyramid, basically. So it has 4 faces which are all the same. And it also has a smaller triangle within the tetrahedron, but still respecting it to hold the egg secure. Now onto velocity, which has all the formulas here that I used, all the symbol meanings, and the units that I used that were given to me, which was just height and the weight of my lander. And down here are the results. I am going to sum this up in my descriptions of my voice so that I don't have to do this twice. So, in freefall, an object's mass under the influence of gravitational force is only affected by gravity. The mass does not play an effect on this. We can find the velocity of an object through the formula given. Velocity is equal to initial velocity plus gravity times time. I did not have time, but I did have the height and, well, the velocity of Earth's gravity, which is 9.80665. In reality, though, a falling object's velocity is constrained by terminal velocity, which is the constant speed that a freely falling object eventually reaches. So, to calculate the time for an object to hit the ground, I used one of the 4 kinematic equations that describe my objects in motion, or that describes any object in motion, which is given there, which is distance is equal to initial velocity times time plus 1/2 acceleration times time squared. And that allowed me to find the initial velocity and time. And as an object falls from rest, its gravitational potential energy is converted to kinetic energy. Conservation of energy as a tool permits the calculation of the velocity right before it hits the surface. This is how it calculated the impact force by using the beginning energy, which is all potential energy, into transferring it into the final energy, which is kinetic energy, which are both equally the same. And it does not depend on mass at all. So, with this, including mass, I was able to find the kinetic energy in joules, which is equal to its initial potential energy, assuming air friction is negligible. In addition, we know that the distance traveled after the impact is 0.1 meters. Then the impact force may be calculated using the work energy principle. And I use that to find the impact force on both drops that you could see here, a meter and 1.5 meters. Which leads back to structural analysis. As I described before, this is my design that eventually I stuck with. So since it's a tetrahedron and has a z displacement of 2.5 right here, I was able to find the coordinates of it in a 3D coordinate plane system by treating it as an equilateral triangle. By finding the distance from one of the from the ground into another leg, which was 10 inches. And I used that angle. I used the fact that it's an equilateral triangle to know that at all angles within this structure, at least of the front faces, are all of 60, which allowed me to find the centroid of the equilateral, and that includes the centroid from the point here and here, which are all shared throughout the structure since it's a tetrahedron. And having that, I was able to use the distance. I was able to use Pythagorean theorem and algebra and maybe a little bit of cal, I suppose, to find the coordinates here by using a ratio of the distance in the z-axis to find the dimensions of the seat for my egg right here. And with that distance, it allowed me to get the coordinates of all the joints in my structure, which are given here. So it's important to remember that my structure is a tetrahedron. So hold on to that, because it basically means all the faces are equilateral and equal to one another. And mirroring, which comes to my egg drop attempts. This is my second attempt. And
second trial of the egg drop. I already showed you guys the height right there, so let's see. This is my little landing pad per se, because I don't want egg splatter anywhere. And it's leveled right there. This is a meter drop.
So my second test did not go so well. It cracked under pressure and failed. The structure did not survive, and nor did the egg land the Eggstranaut. However, it did follow design requirements. Now, after this attempt, I basically thickened it up and made it more secure so that the egg wouldn't
Here is
slip
attempt number
through.
3 at the 1 meter drop. This is a 1 meter distance right here. This is my little protect.
I'm sorry about that.
Okay, here is attempt number 3 at the 1 meter drop. This is a 1 meter distance right here. This is my little protective suit. Let's see if it survives. That's living, baby! Yes, sir, that is alive. Attempt number 3 for the win.
So it completely survived with no issues at all at a 1 meter drop when I doubled the 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 weight of it by making it thicker. Then next was my fourth attempt or fourth test,
Okay,
which
so
raised the height to
it survived the meter
1.5
drop on a
meters.
test 3. So now I have to keep going till this little bad boy breaks. So I decided, hey, let's see if it can survive a 1.5 meter drop. Right here. I don't think that survived. Wait. Barely? It did crack, so I think that is a fail, but it still survived fairly well if you ask me. It didn't splatter all over. I guess that is its
It didn't splatter at
limitations.
all. And yeah, those were the videos of my egg test, which here is a performance table that tells you the test, the weight, if it passed or failed, or and the performance calculation. Give you a moment to look at that. Okay. Now, after it passed, we were given a task to find the forces enacting throughout the structure of one leg. So here I drew out what one leg to look like on my structure, and given the velocity and the force undergoing a certain point after the fall of 1 meter, even 1.5 meter I calculated, it allowed me to find, okay, wait up. Using the coordinates, I was basically able to treat the space thrust in a 2D manner by finding the angle from one of the point on the ground of the leg towards the other points that it's connected to. So treating it like so using these dimensions, I was able to find the angle of each point from C towards E, towards C to D, towards C to F by using dot product, which gave me the angle of C to D to be 42.95 degrees, from C to E to be roughly around 30 degrees, and C to F to be 17.06. So this leg is actually connected towards from here to here, from here to here, and from here to here. So having found the angles, I was able to find the other angles of the truss here by treating it in a 2D manner, using a right angle method to find the angle of here, which allows me to find the force enacted upon my structure. And knowing the force and the angle, I was able to use the the sum of all y and all x method to find the forces enacted throughout each member. From here, I was able to find the forces enacted on member CF by adding the impact force through the leg and using the angles that I found to find the forces enacted through each member. For CF, I got negative 15.10 N, which is newtons, and for the sum of all x, I was able to find the forces enacting on CE, which is 13.077. Important to notice that since this one right here is negative, it is compressed in that member structure, while this is positive, is undergoing tension. So when finding these two, I found these two, so it enabled me to find all of the forces enacting through here, which was BF, which connected towards the other leg, was 14.02636 tension, and allowed me to find FE, which is 2.06.007 N, which is more tension. And this is for the 1 meter. The great thing about the tetrahedron is the fact that since it's treated like an equilateral triangle, I can find the forces enacting from here to here towards, okay, for example, I'm able to find the forces enacting on half of this structure and mirror it onto the other half, since it is equilateral. They share the same angles. And since it's a tetrahedron, it has 4 faces which are all the same. So I'm able to apply it throughout the entire structure to find all of the forces enacting throughout the structure simply by finding just half of one face, because it's all equilateral. That's why I told you it was important, because applying this knowledge, I was able to find the calculations of all the forces enacting on all the members of my structure for both the 1 meter and the meter. This side right here is a meter. This side over here is 1.5 meters. So this is the forces of all of them, of every member throughout the structure, for 1 meter and then 1.5 meters. The beauty of the tetrahedron. So, which leads me next to the verification of my structure. This is the landing pad, and this is what it looks like in my hand. Here is the measurement of the landing pad to prove that it fits within the structure, the guidelines, and the weight added of my structure and the egg, while proving that it did fall at the distance seen in my duct tape under the, it's the correct measurements the duct tape on my wall was to indicate my points of dropping my lander. So, in conclusion, I brainstormed and built a Mars lander out of spaghetti that I dropped from multiple heights to test its structural security and safety for my Eggstranaut. Then proceeded to calculate all the forces enacting on it by finding the velocity and the initial impact, which required a structural analysis. And because it's a tetrahedron, I was able to find all the forces enacting on my structure. And yeah, I think that concludes my project. I hope you have a great day. Farewell.